Hello, everyone. We're the NASA Seas Aerospace team, and we have designed Enso-Sat, which stands for El Niño Southern Oscillation Satellite. Here are all the members of the aerospace engineering team.
My name is Catherine Clay, and I am from San Antonio, Texas.
Hi, my name is Jordan Cochran, and I'm from Columbia, South Carolina.
My name is Kyla Hunter, and I'm from Flowood, Mississippi.
Hi, my name is Praga Kalatheeswaran, and I'm from Bridgewater, New Jersey.
Hi, my name is Mary Lay, and I am from Portland, Oregon.
I'm Aparna Majety, and I'm from Austin, Texas.
Hi, my name is Rithvik, and I'm from Ashburn, Virginia.
Hello, my name is Rivera as part of the Seas Aerospace engineering team. I go to City Honor.
Hi, my name is Yovanny Vasquez, and I am from Charlottesville, Virginia.
Our broad goal is to research global warming and climate change by monitoring El Niño, also known as El Niño Southern Oscillations, or ENSO, which is an irregularly occurring natural phenomenon that mainly occurs in the Pacific Ocean every 2 to 7 years. This will be done by monitoring a variety of environmental factors, including sea level rise, tropical storms, and greenhouse gas emissions.
El Niño, also known as El Niño Southern Oscillation, or ENSO, is a natural phenomenon that mainly occurs in the Pacific Ocean every 2 to 7 years, lasting 9 to 12 months, and can affect weather worldwide. The ENSO cycle is made up of El Niño and La Niña, which are opposite phases, and the ENSO cycle is a scientific term that describes the fluctuations in temperature between ocean and atmosphere in the east-central equatorial Pacific. Scientists today can only predict El Niño 6 months to a year before it takes place. The effects of this weather phenomenon include severe drought, flooding, and etc. In North America, El Niño often results in warmer than average temperatures over western and central Canada, and over the western and northern U.S. In addition, drier than average conditions can be expected in Ohio Valley and the Pacific Northwest. Some of the weather effects include landslides, storms, flooding in California, and even crop damage. There have been increased wildfires in southern Mexico and Central America. The benefit to studying El Niño weather phenomenon is to understand the global climate system, since El Niño has such a large ripple effect. Due to greenhouse gas emissions, extreme El Niño events may increase more frequently. For example, global warming can cause El Niño events to shift eastward along the equator in the Pacific Ocean. This was shown through the 2015 through 2016 Super El Niño. During this time, more than 60 million people were affected, and more than $3.6 billion went into helping the humanitarian response. These changing weather patterns can have disastrous effects on agriculture, ecosystems, air quality, and much more.
El Niño was first recorded in 1525 by Spanish conquistador Francisco Pizarro, when he noticed abnormal desert rainfall in northern Peru. The weather phenomenon eventually received its name during the 19th century as fishermen in Peru observed the way the warm water flowed south during Christmas time. El Niño is Spanish for the boy child, or the Christ child, and is also referred to as El Niño Southern Oscillation, also known as ENSO. The Southern Oscillation originated from Sir Gilbert Walker in the 1930s, as he noticed the pattern of interannual change in the tropical atmosphere. The most recent ENSO was in 2018 to 2019, but the strongest years recorded were 1982, 1997, and 2015. The 1982 El Niño brought about the rise of the bubonic plague in New Mexico, abnormal temperature rise in Alaska and Canada, and a shift in Earth's angular momentum, which increased the day's length by 0.2 milliseconds in late January. The 1997 El Niño left 16% of the world's breeze systems destroyed, increased the temperature in the air by 1.5 degrees Celsius. During the water season, California saw record rainfalls, and Indonesia marked the year to be one of its worst droughts in its history. The 2015 El Niño produced widespread drought across the globe, along with strong floods. Despite the predictions that ENSO would get weaker over time, it instead continued to get stronger throughout the year. In 2015, ocean temperatures rose more than 2 degrees Celsius in the Niño 3.4 region. The phenomenon also triggered disease outbreaks such as hantavirus, cholera, and dengue fever in Colorado, Tanzania, and Brazil. Indonesia is typically known to be one of the rainiest places in the world. However, during the 2015 El Niño, drought led to large fires and produced a disproportionate amount of smoke. The aftermath of the fires lowered the air quality for Indonesia and its surrounding areas. The 1998 Enso produced large amounts of rain in North and South America, along with dry weather throughout the rest of the world. The ocean temperature rose about 3.6 degrees Fahrenheit during the fall. As you can see in the picture, landslides, drought, rain, and famine were the aftermath effects of this weather phenomenon. Nicaragua also faced a large drought because the average percent of rain dropped 75%, also affecting the farmers and the economy. This caused the production of meat and dairy to fall as the prices for them continued to rise. In 2016, more than 31 million people in China were affected by floods triggered by El Niño. It was recorded to be the worst flood since 1998, submerging 6.7 million acres of cropland and destroying major farms.
Current conditions. Despite the onset of an El Niño and the UK Met Office scientists forecasting a cooler year in the Pacific Northwest, Oregon saw record-breaking high temperatures and alarming increased drought conditions as a result of greenhouse gas influence. Researchers from the World Weather Attribution, peer-reviewed, write that the observed temperatures were so extreme that they lie far outside the range of historically observed temperatures. A new analysis found that these conditions would have been virtually impossible without human-caused climate change. This past heat wave killed 116 people in Oregon. Multnomah County makes up for Oregon's highest death toll with 54 confirmed and 17 suspected hypothermia deaths. And for context, prior to the heat wave, the county had just 2 deaths from heat in the past 20 years. With an El Niño on the rise, conditions will only become more severe. Given time constraints and current local housing under-equipped for heat, such weather conditions prove to be deadly, especially to the most vulnerable population experiencing homelessness. Mission overview. The mission itself is to design an Earth-observing satellite with consideration to several factors, starting with a picture on the top right that compares the movement of warm and cold water in a normal year and in an El Niño year. El Niño southern oscillation is the warming of the ocean surface or above average sea surface temperatures in the central and eastern tropical Pacific Ocean. This warming causes a shift in the atmospheric circulation, with rainfall becoming reduced over Indonesia, India, and Australia, while rainfall in tropical cyclone formation increases over the tropical Pacific Ocean. The low-level surface trade winds, which normally blow from east to west along the equator, either weaken or start blowing from the other direction. The picture below on the right shows a country in East Africa facing the devastating effects of the El Niño weather phenomenon. Several East African nations reported much heavier rainfall this rainy season, which many experts say is due to changing weather patterns. The mission designed by our team covers research and understanding of the Enso cycle and the development of a satellite that monitors this weather phenomenon. The satellite has been designed with consideration to the launch, the orbit, and the data that is monitored, as you can see from the picture of the ground tracks, a sketch of the satellite, and a launch rocket.
We created a list of mission requirements for our mission, which outlines what the satellite and its instruments shall do while the satellite is in orbit around the Earth. These requirements include observing the El Niño phenomenon, covering plus or minus 60 degrees in latitude, monitoring sea level changes, reporting tropical storms, monitoring atmospheric carbon dioxide, having a design lifespan of 15 years, and having a launch mass of no more than 2,300 kilograms. Some additional requirements pertain to the specifics of the mission, such as the altitude at which the satellite will orbit at, where the satellite will launch from, and the amount of power the satellite will generate by the end of its life. These requirements ensure that the satellite is able to obtain the appropriate data for the planned amount of time, and that it is able to transmit this data down to Earth so that it could aid in the research of El Niño. This is a conceptual model of the Enso-Sat, which was created using computer-aided design. The body of the satellite measures 3 meters by 2 meters, and the solar panels on both sides are able to rotate so as to constantly face the sun. As can be seen in this model, the Poseidon 3 radar altimeter always points nadir, or downwards towards the Earth. An additional instrument that can be seen is the Tanso FTS sensor.
We plan to launch our rocket from Kennedy Space Center in Florida utilizing a SpaceX Falcon 9 rocket. Our satellite will be launched into an orbit with an altitude of 800 kilometers, an inclination of 60 degrees, and a period of about 101 minutes. Our satellite will have a payload mass of 633 kilograms and a total mass of 2,274 kilograms. At the end of its use, we plan to deorbit our rocket using an onboard booster.
Using our satellite, we will monitor sea level rise, greenhouse gases, and weather. To monitor sea level rise, we will be using the Poseidon 3B radar altimeter on the Jason 3 satellite. Jason 3 is an international mission which was launched on January 17, 2016 in Vandenberg to gain more understanding on ocean circulation and climate change. It is currently active and makes detailed measurements on the height of the ocean surface, which provides information on changes in sea level and circulation. Tracking sea level using altimeter data can help predict El Niño, which gives rise to warmer sea temperatures in the eastern tropics, causing higher sea levels. Poseidon 3B is a radar altimeter that calculates aspects of the ocean, including wave height and ocean surface current velocity, by emitting a radar beam that gets reflected from the Earth's surface and back to the antenna. It also tracks ocean topography, sea level rise, and gravity field through two frequencies at 5.3 and 13.58 gigahertz. Its radar antenna has a diameter of 1.2 meters, which samples at 30 kilometer intervals along track. The average data rate for this instrument is 37 kilobits per second with a mass of 70 kilograms and a power of 78 watts. This image captures the sea level rise from December 1997 and 2015 from the Jason 3 satellite. The red area represents higher sea levels, while the purple regions represent lower sea levels. Our next environmental factor that we will monitor are the greenhouse gases. To monitor greenhouse gases, we will be using TANSO FTS2, which stands for Thermal and Near-Infrared Sensor for Carbon Observation, Fourier Transform Spectrometer 2. This is used on the GOSAT-2 satellite to measure greenhouse gas concentrations, specifically carbon dioxide, methane, and carbon monoxide with extremely high accuracy. The GOSAT-2 was a follow on the GOSAT satellite, which was a greenhouse gas observing satellite originally launched on January 23, 2009 as a joint project between the Japan Aerospace Exploration Agency and the National Institute of Environmental Studies. This satellite's primary mission is to measure carbon dioxide and methane in the Earth's atmosphere using TANSO FTS2. This instrument allows scientists to discriminate between natural and man-made emissions by measuring shortwave infrared sunlight reflecting from the ocean. It has a mass of 255 kilograms and a power of 187.2 watts.
Our final factor to monitor is weather, and the ABI will assist us in this. The ABI, or the Advanced Baseline Imager, observes Earth's surface, atmosphere, and cloud cover, but more precisely, its oceans and weather. It has a multi-channel passive imagery radiometer designed to record and provide variable error imagery and radiometric information. This is also a primary instrument of the Geostationary Operational Environmental Satellites, or series. It has a mass of 338 kilograms and 450 watts in power.
This graphic shows the makeup of our satellite's mass and the percentage of each separate subsystem. The wiring, thermal, and telemetry tracking and control subsystems each account for about 4% and 90 kilograms of our satellite's total mass. The altitude and orbit control subsystem makes up 7%, or about 158 kilograms of the satellite's total mass. This subsystem will help ensure that our satellite is always nadir pointing. The propulsion system will aid in maneuvering the satellite and will be used to deorbit the satellite at its end of use. It accounts for about 12% and 286 kilograms of the satellite's total mass. The structure subsystem of our satellite has a mass of 407 kilograms and is 18% of the satellite's total mass. The second largest subsystem on our satellite is the power subsystem. It includes solar panels and battery packs that will power our satellite. It has a mass of about 520 kilograms and is 23% of the satellite's total mass. The largest subsystem is the satellite's payload. It is 28% and 633 kilograms of the satellite's total mass. In the center of the graphic, the total mass of our satellite is displayed.
Power is necessary in any satellite, and this is our power system. Our satellite needs 905 watts of power, and for times when light is scarce, Enso-Sat will have a battery with a capacity of 1.7 kilowatt hours. To accommodate for charging the battery while powering the satellite, Enso-Sat will have 10 square meters of solar panels.
To dispose of our satellite, we will implement a two-burn Hotman transfer utilizing a coal gas powered booster. The Hotman transfer will deorbit our satellite to an altitude of 146 kilometers, where it will eventually burn up due to atmospheric drag. The booster will likely be powered by CO2, similar to those used on the GRACE mission. No longer functioning satellites are left in orbit, which serves as space debris. This negatively affects the planet as well as space exploration by potentially leading to in-space collisions. Additionally, large enough pieces of space debris left in a low orbit can strike the planet's surface.
Some of the challenges that we had to overcome during our time with this internship really included working with new technologies that we had never seen before, like TK Solver, which is an orbital mechanics calculation software. Additionally, we had to learn new fields of science, such as orbital mechanics, because we're working with satellites, which is something that none of us have actually worked with before. So it was really interesting to get that group learning experience. Additionally, we had to grapple with advocating for our team and also coordinating our team. So coordinating schedules, we're all across the country, so it's very difficult to find times that work for all of us, but I think that my team did a very good job of this. And advocating for our skills and our abilities to scientific journals, which is something that we're doing, which sort of goes above and beyond the standard project. So yeah, so those are some of the challenges that we face as a team, but I think we did a very good job, and I think all of the team members left with a better understanding of what it means to be a productive member of a research team.
Furthermore, our team was excited to work in a collaborative research environment with other like-minded high schoolers who have similar goals and aspirations. Finally, I would like to say thank you. We would like to express our deepest gratitude to Dr. Wallace Fowler for his guidance, knowledge, and unwavering support in our journey to designing our satellite. We would also like to thank Dr. Teresa Howard, Selena Miller, and the SEA staff for providing this unique opportunity. Thank you.